Hey everyone, so in this video we're going to be talking about categorical and numerical data. So let's talk about what each one is. So first let's talk about categorical data. Now categorical data is also known as qualitative data, but I'm going to refer to it as categorical data for the remainder of this presentation. And categorical data is non-numerical data that could be separated into categories. So examples of this would be eye color or gender or flavor of ice cream, things that could be separated into categories, things that aren't necessarily numeric. And then we also have numerical data, which is also known as quantitative data. And I'm going to refer to this as numerical for the remainder of this presentation instead of quantitative. And the reason why I'm referring to these as categorical and numerical is because they're a little bit more intuitive to understand, and because quantitative and qualitative sound so similar that it'll be easier to distinguish between the two if I just say categorical and numerical. So numerical data is numeric in nature, and we have two different types of numerical data. The first type of numerical data is called discrete. And numerical data is said to be discrete if the set of all possible values is finite or countably infinite. So that sounds super fancy, but all that means is that we're able to count this type of data. So examples of this would be page count, or the number of people in a room, or the number of home runs a baseball player hits in a season, or the number of test questions answered correctly. These are things that can be counted. So for example, with the home run total example, a player could hit 21 home runs, or 22 home runs, or 23 home runs. The player can't hit 21 and a half home runs or 21.03 home runs. It's something that you can count, 0, 1, 2, 3. There are gaps in between those numbers. So a data set's continuous if the set of all possible values is an interval of numbers. So we talked about how discrete can be counted, but continuous is more measured. So examples of this would be height or weight or temperature. These are intervals and they don't exactly have gaps between the numbers like the discrete data did. So just a couple things to be careful of here. Just because data values are presented as numbers, it does not automatically mean that they're numerical. And the very best example of this would be zip codes. Zip codes are numbers, but they're categorical. And then the other thing we want to be careful of here is that numerical data can be continuous in nature, but it could be presented in a discrete way. So for example, we could say the amount of rainfall tomorrow is continuous, but the amount of rainfall in inches is discrete. So if we were to round this to the nearest inch of rainfall, then it would become discrete because then there would be gaps in between those numbers. So when we have categorical data, a common way to summarize it is using what's called a frequency distribution. And a frequency distribution displays the distribution of frequencies. So it's a really nice name for it. It's just a table that displays the frequency of various outcomes in a sample. So for example, let's say we gather information about eye colors of 20 people and we end up with this. So let's say the first person we talked to had blue eyes, the next person we talked to had brown eyes, the next person after that had blue eyes, and so on. So what we could do is we can count the number of people who had blue eyes, we could count the number of people who had brown eyes, and do that for all the colors, and we would end up with something like this. So this means that we found 9 out of the 20 people who had brown eyes, and similarly, we had 7 people who had blue eyes. So if we carry this frequency distribution over to this page, this is the same thing from the previous slide, we would have this, and we could turn this into what's called a frequency bar chart. Now, a frequency bar chart gives a visual representation of the frequency distribution. So it's going to look something like this. So since we had 9 people with brown eyes, this bar is going to have a height of 9. And we had 7 people with blue eyes, so the height of this bar is going to be 7. So now let's talk about what are called relative frequencies. And a relative frequency is the frequency divided by the total number of observations. So this is just nothing more than the fraction of times a certain observation occurs in a sample. So all relative frequencies from a sample should add up to 1. So an example of a relative frequency from the eye color example, we had 9 people out of the 20 who had brown eyes. So our relative frequency is going to be 9 divided by 20, or 0.45. So if we convert all the eye colors into relative frequencies, we would have something like this, and this is known as a relative frequency distribution. So remember, with brown, our relative frequency was 0.45. If we did the same thing with blue, we had 7 people who had blue eyes and 20 people altogether. So our relative frequency is going to be 0.35. And we can do this for all the eye colors that we came up with. So just like before, we could turn this into a relative frequency bar chart. So 0.45 was our relative frequency for brown, so the height of this bar is going to be 0.45. Similarly, with blue, our relative frequency was 0.35, so the height of this bar is going to be 0.35. So you might notice that this relative frequency bar chart here looks the exact same as the frequency bar chart. And in fact, this is always the case. The relative frequency bar chart and the frequency bar chart are going to look the exact same. The only difference is that our y-axis is going to be rescaled, because all we really did was take each number and divide it by 20. So relative to each other, they are the same size. So this is going to look the same. The only difference is the y-axis here. So that was how we handled categorical data for that situation, but now let's talk about how we handled numerical data for that same situation. So we can construct a frequency distribution just like we did with the categorical data, but there are going to be some small differences here. So in the frequency distribution, since this is numerical data, we're going to have to make sure that this is in order. You usually can't order the categorical data, but with numerical data, we have to be careful of that. So visually, instead of a bar chart, we're going to use what's called a histogram. And histograms actually look pretty similar to bar charts, but the only difference is that there are going to be no gaps in between the bars, and the bars are going to be touching each other. And we'll look at an example of this in a little bit. So let's look at an example. So suppose we're interested in making a histogram of the run totals for each MLB team during the 2019 MLB season. So here's a list of all the run totals for each MLB team during that season. So what we do is we're actually going to group these into what are called bins. So we're going to look at all the teams that had between 550 and 600 runs, and then all the teams that had 600 to 650 runs, and so on. And we're going to count how many fell into each of these intervals. So it looks like there was only one team that had between 550 and 600 runs, so we're going to put a 1 there. Similarly, there was only one team that had between 600 and 650 runs, and that's right here. So we're going to put a 1 here. And we can go on down the line, and then we'll end up with something like this, and this is a frequency distribution, but with numerical data instead of categorical. So if we carry this frequency distribution over to the next slide, we'll have this up here, and then we can construct what's called a frequency histogram. And a frequency histogram is the same thing as a frequency bar chart, except this time these bars are going to be touching each other because we have numerical data and we need to show that there is an order here. So this is constructed in the same way. So we have a 1 here, so the height of this bar is going to be 1. And then we have a 1 here, so the height of this bar is going to be 1. And then we have a 3 here, so the height of this bar is going to be 3. And then we can do this for all the totals, and we'll end up with a histogram that looks something like this. So we could do the same thing with the relative frequencies and construct a relative frequency histogram. So we have 30 MLB teams from that sample. So we're going to divide each of these values by 30 here. And if we do that, we'll come up with a relative frequency distribution that looks something like this. So just like before, we can turn this into a relative frequency histogram. And also just like before, notice that this doesn't look any different from the frequency histogram. So if I go back and forth between these slides, you'll notice that they don't look any different from each other. And again, the only difference here is that this y-axis is rescaled, because also just like before, all we did was divide each of these values by 30. So the height of the bars relative to each other is not going to change. So anyway, that's it for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.